Welcome to Archi Talk Shop. Today we're going to look into different types of iconic building constructions around the world, and we will be going to uncover their iconic stories. हम मोस्टली उनके कंस्ट्रक्शन साइड ऑफ द थिंग्स के बारे में बात करेंगे जिसमें ज़्यादा टेक्निक्स और मटेरियल यूटिलाइजेशन आ जाती है और द चैलेंजेस द डिज़ाइनर हैज़ फेस्ड और उन डिज़ाइनर्स ने उन चैलेंजेस को कैसे टैकल किया था. Each of these structures marks some major milestone in architectural history and highlights some really creative problem solving. Now let me introduce Jimena and Anusha, and they will take us through the fascinating details of these amazing. The Sagrada Familia is a famous basilica in Barcelona, Spain, designed by the renowned architect Antoni Gaudí. इसकी construction 1882 को शुरू हुई थी and it still continues to this day, making it one of the longest running architectural projects in the history. The basilica is a masterpiece of Catalan modernism combining Gothic and Art Nouveau elements. Its design is inspired by nature, featuring intricate carvings of plants, animals, and symbolic figures. The basilica has 18 towers in total, all of them representing something from Christianity. Out of these 18 towers, 12 represent the apostles, the four evangelists, one for the Virgin Mary, and lastly, the tallest tower that is still under construction will represent Jesus Christ. Interior of the basilica consists of colorful stained glass windows that fills the space with vibrant light, creating a serene atmosphere. Gaudi's innovative use of geometry and organic forms give the building a unique, otherworldly appearance. Declared a UNESCO World Heritage Site, the Sagrada Familia is not only a religious symbol but also a testament to artistic vision and perseverance, drawing millions of visitors annually.
Talking about the structural design and innovations of Sagrada Familia, its structure relies heavily on the use of parabolic arches, catenary curves, and hyperboloids. As for the catenary curves, they are basically hanging chains that take shape of a catenary arch and they have load only at their ends. And the hyperboloids are basically structures that are built on a surface that is formed by rotating a hyperbolic curve around its axis. These forms create natural load paths, making the basilica self supporting without the need for traditional flying buttresses. Gaudi's use of double curved surfaces and branching columns mirrors natural systems, ensuring both stability and aesthetic harmony.
If we are going to talk about the construction techniques used in Sagrada Familia, Gaudi introduced modular construction techniques long before the modern day adoption. Many elements of the Sagrada Familia, such as its intricate facade and spires, they are prefabricated off-site and assembled on-site, like puzzle pieces. And इससे ये होता है, the construction process speeds up, as the building has been under construction since the last 140 years, a long time. The prefabrication has significantly accelerated construction. Gauri used innovative technique to design the building structure. Unlike most architects, he utilized physical models instead of detailed drawing. He created upside down hanging chain models जिसमें calculation होती है forces of gravity and stress की that ensures the stability of the basilica's intricate arches, vaults and towers that are aesthetically pleasing and structurally strong. Ab as technology has advanced, modern construction teams use 3D scanning and parametric modeling to replicate these shapes with high precision. Gaudi's architecture is one of a kind. His work transcends mainstream modernism and culminates into a distinct style, जो कि inspired है by nature. The church is a complex structure with unique elements, जैसा कि जुमैना ने भी brief किया था, with tree-like columns, hyperboloids and paraboloids in arches, walls and windows, catenary arches, twisting and towering spires, ceiling adorned with star patterns that mimic the night sky, helical staircases inspired from the famous Fibonacci golden ratio that is found in nature, and organic ornamentation both in interior and on the facade and exterior as well. These elements make the structure complex and heavy. अगर हम load bearing की बात करें, unlike most neo-Gothic churches, it does not utilize a flying buttress. Basilica के columns इस तरीके से डिजाइन किए गए हैं that dynamically bear the load of the structure by changing their width and angle, mimicking the way trees distribute weights in nature. This innovation made the towering structure both stable and visually stunning. The facade and ornamentation heavily utilizes stone. First done manually and then over time, the project transitioned to using computer-guided stone cutting machine. This allows precise carving of complex geometries that aligned with Gaudí's organic, nature-inspired design. Statistically, the basilica is the third tallest in the world, and by the time of its completion in 2026, it would be the tallest church in the whole world. The central towers, including the 570 feet spire of Jesus Christ, which is still under construction, these towers are built using a specially formulated lightweight reinforced concrete. This reduces the weight of the towering structure while simultaneously ensuring durability and resistance to weathering.
The basilica facade has interesting details, specific columns that resemble trees in varying materials, like colorful glass. Can you please reflect on the materials utilized during the construction?
As for the construction materials that were used in building Sagrada Familia, initially the idea was to use the local Montjuic sandstone, which is obtained from Jewish mountain. But due to its limited availability, other stones like granite, basalt, and reinforced concrete were introduced. Reinforced concrete allowed for lighter yet stronger elements, while the intricate detailing uses ceramic tiles, mosaic glass, and iron. In terms of durability, the Montjuic sandstone weathers over time, but under extreme conditions it is not very durable, while concrete allows thinner structures to be built that are more strong. Still, we would observe that the earlier parts of Sagrada Familia are built by the Montjuic sandstone. The stone used for the bell towers on the Nativity and Passion facades is sandstone from Montjuic in Barcelona. Another material that is used is the red porphyry. Porphyry is basically a hard igneous rock that contains crystals of feldspar in a fine grained groundmass. It is found in Iran, and because of its red color, it is used as a symbol of the blood of Jesus Christ. Plus, its hardness and strength makes it perfect for the four columns on the crossing of the basilica and the flooring of basilica. The other materials used in the construction of Sagrada Familia include concrete, stone, wood, and glass. The primary materials used for Sagrada Familia are concrete and steel.
अगर हम historically timeline में देखें, the construction of the basilica and the Spanish Civil War, they overlap with each other. Did that cause any hindrance in the construction?
In the early days of Sagrada Familia, when the construction just had gained momentum, Gaudí tragically passed away in a tram accident. His work, the basilica, was barely quarter of the way complete. Relying solely on private donation, the Sagrada Familia's construction progressed slowly, and then it was interrupted by the Spanish Civil War in 1936. Many of Gaudí's original blueprints, models, and drawings were destroyed. This created significant challenges for future architects who had to reconstruct his vision based on surviving fragments and written descriptions. Each generation of architects and builders had to interpret and adapt Gaudí's incomplete plans, which has occasionally led to debates and delays. The project has been under construction for over 140 years, जिसकी वजह lack of funding and lack of mutual decision है. Gaudí का vision and design were far ahead of his time, and many elements of the basilica were almost impossible to construct with the 19th century technology they had back then. Only modern advancements such as computer modeling and CNC machines have allowed builder to realize his intricate design. एक unique structural problem ये है, the whole concept is very ambitious. The towering heights and unconventional design like hyperboloid walls and twisting spires, they pose a significant engineering challenge. Builders had to develop new techniques and material to ensure the basilica could bear its immense weight and withstand natural forces. In total, there will be 18 towers, out of which 13 are already built. The highest tower, the spire of Jesus Christ, will reach up to 570 feet. The vertical loads from these massive towers require the use of reinforced concrete columns with embedded steel cores. The basilica's size and ongoing expansion have caused logistical problems in the surrounding urban area. As the church completely dominates Barcelona की skyline, वहाँ के लोग have their concerns. Specifically, urban integration issues. अगर हम example लें, the church is situated in the city center of Barcelona, and the infrastructure of Barcelona had planned to build a tunnel for a nearby high-speed rail line. Concerns arose as it risked destabilizing the building's foundation. Special precautions had to be implemented by the government of Barcelona to prevent structural damage, while the foundations were strengthened to ensure seismic stability.
Looking at the aesthetical aspects and how the Sagrada Familia's structure was integrated with the environment, you will observe that Gaudí used stained glass windows that are not just decorative, they are strategically placed to diffuse light evenly. It also reduces the solar heat gain and allows controlled daylight into interior spaces. It creates a serene and peaceful environment. This design keeps the basilica naturally illuminated and thermally comfortable.
Sagrada Familia is a living testament to how historical craftsmanship and modern engineering can come together to create something extraordinary. The Burj Khalifa, located in Dubai, is the tallest building in the world, standing at a staggering height of 2,717 feet. Completed in 2010, it was designed by the architectural firm Skidmore, Owings and Merrill, led by Adrian Smith. The building's design is inspired by Islamic architecture, particularly the spiral shape of the Hymenocallis flower, and incorporates advanced engineering to withstand Dubai's desert climate and strong winds. The Burj Khalifa serves as a mixed-use skyscraper. इसके अंदर housing luxury apartments हैं, offices हैं, like Armani Hotel है, or of course the observation decks offering breathtaking views of the city's skyline. Its innovative Y-shaped floor plan maximizes space and stability. Clad in reflective glass and aluminum, the structure glimmers in the sunlight, symbolizing Dubai's ambition and modernity. Beyond its architectural significance, the Burj Khalifa is a global icon, attracting millions of visitors and representing a landmark achievement in human engineering and
The
design.
Burj Khalifa uses a groundbreaking structural system that enable it to reach its incredible height of 2,717 feet. Firstly, it utilizes a buttress core design. The buttress core system is the primary structural innovation that gives Burj Khalifa its immense height and stability. Here's how it works. The central core. The central reinforced concrete core is the backbone of the structure. It houses elevator, stairwell, and all the other essential services. This core acts as a vertical spine, providing support and resisting gravity and lateral forces like wind and seismic activities. From this central core, three wings extend outwards at 120 degrees, forming a Y shape. These wings buttresses the central core, meaning they support and stabilize it by resisting wind force and preventing twisting. The wings also distribute the building's weight evenly to the foundation. As the building rises, the wing taper and step back into a spiraling pattern. This design reduces the wind loads by confusing wind currents, breaking up vortex shedding. That is, it prevents the oscillation caused by the wind. The Y-shaped floor plan is an essential part of the buttressed core system, offering both structural and functional benefits. The Y-shape spreads the load of the building across three wings, reducing pressure on any single point and ensuring balance and stability. This layout enhances the building's ability to resist lateral forces, especially the strong desert winds. The Y-shaped plan creates a staggering stepping effect as the tower narrows, deflecting wind around the structure instead of allowing it to push against flat surfaces, and gives it an aerodynamic advantage. The three wings provide more corner rooms, which are highly desirable in luxury skyscrapers for their panoramic views, and it maximizes usable space. The layout also optimizes floor area while maintaining structural efficiency. Y-shape ensures that every part of the building is no more than 30 meters from the central core, facilitating efficient elevator access and mechanical services. Why is this buttress core design so special? The buttress core design, combined with the Y-shaped floor plan, allows Burj Khalifa to achieve its record breaking height while remaining stable and functional. This combination is not only a marvel of engineering but also a work of architectural elegance balancing form and function seamlessly. Burj Khalifa is also the world's tallest reinforced concrete building. Unlike many other superstructures that rely on steel frame, the Burj Khalifa achieved its record-breaking height primarily with reinforced concrete up to its
जैसे
spire.
कि हमें पता है, the deeper the roots of the tree, the stronger it is. For a building that's hundreds of meters high, the construction of the foundation must require a lot of engineering marvel. Can you elaborate more onto this?
Obviously, for a building that huge and hundreds of meters high, it definitely would have took a lot of technicalities to be brought under consideration, especially its foundation, because as you know that the stronger a building's foundation, the more stable and enduring it will be. The foundation of Burj Khalifa alone took over an year to complete due to Dubai's challenging soil conditions. Dubai's terrain is dominated by loose desert sands which lack cohesion and are prone to shifting. This makes it difficult to establish a stable foundation for heavy structures. The building sits on a 3.7-meter thick reinforced concrete mat which is supported by 192 board piles. Board piles are cylindrical bodies that are made of concrete. They can be with or without reinforcement. They are installed in the ground by a variety of methods. As for Burj Khalifa, each pile is 50 meters deep and reinforced with high strength steel, transferring the enormous weight to the bedrock.
The Burj Khalifa utilizes a combination of advanced material, carefully chosen for their strength, durability, and suitability for the structure's extreme height and climate. Here is an overview of the key material used. The main structural material for the lower and mid section of the Burj Khalifa is high performance reinforced concrete. It is a special concrete mix that was specifically designed to withstand Dubai's extreme temperature and resist cracking. It includes additive like silica fume to enhance strength and durability. Over 330,000 cubic meters of concrete were used, weighing more than 110,000 tons. In the upper sections of the tower, steel is primarily used, particularly in the spire and its supporting framework. The spire is constructed with lightweight structural steel to minimize weight and reduce stress on the building. About 39,000 tons of steel reinforcement were used throughout the structure. The exterior of the Burj Khalifa is clad in a curtain wall system of reflective aluminum panels and glass. Over 103,000 square meter or 1.1 million square feet of glass were used. The glass is double layered and reflective, designed to reduce heat absorption and glare in Dubai's desert climate. Stainless steel finishes and aluminum framing enhances the building's thermal and aesthetic property. Stainless steel was chosen for its corrosion resistance and sleek modern appearance. Marble and stone are used for interior to give luxurious finishes inside the lobbies, residence, and hotel areas. High-end wood veneers and brushed metal panels enhance the interior sophistication. All materials, especially glass and concrete, were engineered to handle temperature fluctuation in Dubai's hot desert climate. The reflective material used in the cladding help reduces the building's energy consumption by minimizing heat absorption. This thoughtful selection of materials ensure the Burj Khalifa's structural integrity, aesthetic appeal, and
A
efficiency.
building this high has never been constructed before, and pehle these heights seemed impossible. What innovative techniques make constructing the Burj Khalifa possible?
One of the innovative techniques used was concrete pumping. Concrete pumping was a groundbreaking feat. Specialized pumps lifted concrete over 600 meters in height, setting a world record. Concrete pumping is basically a process of transferring liquid concrete from a mixing truck to a specific location on the construction site. This was done at night to ensure optimal curing in Dubai's harsh climate.
The Burj Khalifa has a staggering height of 2,717 feet. At such heights, the skyscraper are vulnerable to air forces such as wind pressure and turbulence. इतने फोर्सेस को टैकल करने के लिए इंजीनियर्स ने क्या क्या
Wind
किया था?
speed in Dubai can reach up to 200 km per hour. The Burj Khalifa was designed and engineered to withstand such high speed winds with a safety factor built into the design and to handle extreme weather events at such extreme heights. The unique shape of the structure and advanced wind engineering technique ensure its stability and safety. Here is how it was achieved in the design. The building has an aerodynamic tapered design. It tapers as it rises, with setback at varying heights. These setbacks create a spiral effect जो कि wind forces को disrupt करता है. It was designed on purpose to prevent vortex shedding, a phenomenon where wind creates oscillating force that would cause a building to sway. The tower's asymmetrical Y-shaped floor plan also plays a key role in minimizing wind loads, as it prevents uniform wind pressure on any side. The wind loads decrease as the building narrows. The upper section, including the spire, face less wind pressure due to the smaller surface area and lightweight design. The engineers tested the design with extensive wind tunnel studies. The Burj Khalifa underwent over 40 wind tunnel tests during its design phase, withstanding wind speed up to 150 km per hour. The test includes aerodynamic shape optimization, cladding resistance to ensure the glass and aluminum exterior could withstand strong winds, simulation of wind behavior during construction phases, ensuring stability at each stage. The three wings of the tower are arranged in a rotational pattern around the central core. As each tier steps back, the alignment of the wing carefully changes slightly. This shifting geometry disrupts wind vortices, preventing them from becoming synchronized and reduce lateral forces of the building. Structural ramping through design eliminates need for traditional tuned mass damper by relying on its aerodynamic form to naturally minimize swaying. The building's stiffness and the way the mass is distributed counteracts wind-induced movement. The use of high-strength material also provides the necessary rigidity and flexibility to absorb and dissipate wind energy effectively. Aerodynamics were critical in both the design and construction phase, ensuring safety at each and every stage. By accounting for wind forces early, the architects and engineer could avoid costly structural modification later in the process. This approach not only provides stability but also allows for a record breaking height without compromising safety or comfort.
As we all know that for an architect when designing a building, it is extremely important to add sustainability features or to bring them under consideration. Even at such large a scale, the architects of Burj Khalifa ensured to add sustainable features. The air conditioning system condenses humid air, collecting over 15 million gallons of water annually. It is one of the leading environmental features that it saves water from its air conditioning system and redistributes it for land irrigation and the building's showpiece fountain. The Burj Khalifa is an example of a building that embraces the green agenda and circular economy. The tower is covered in solar panels which heat more than 140,000 liters of water every day. In turn, this water is used by residents and businesses daily. Additionally, the reflective facade and advanced shading systems reduce cooling requirements, making it more energy efficient.
The Burj Khalifa is not just a skyscraper, it's a marvel of engineering combining advanced construction methods with sustainable practices. Located in the city of Pisa, Italy, is one of the most famous architectural landmarks in the world, the Leaning Tower of Pisa. Constructed as the bell tower for the nearby Pisa Cathedral, its construction began in 1173 and spanned nearly 200 years due to the interruptions. The tower's iconic tilt, which gave it its name, resulted from the soft, unstable soil beneath its foundation. Standing at approximately 84 feet tall, the tower features a cylindrical structure made of white and gray marble with 8 stories, including the bell chamber. Its Romanesque design includes intricate arches and columns, showcasing medieval Italian craftsmanship. ये टावर एक declared UNESCO World Heritage Site है. It is a symbol of human ingenuity and perseverance. Millions of tourists annually come and visit the Pisa Cathedral just to see this tower. What was the original construction flaw of this tower that led it from a mistake se mozza tak ka
The
safar?
Tower of Pisa is a part of the Pisa Cathedral. Its construction began in 1173. The Leaning Tower of Pisa was primarily constructed using white and grey marble. It gives it iconic Romanesque appearance. Marble, which is sourced from nearby quarries like Carrara, was used for the exterior, including the columns, arches, and decorative elements. Limestone blocks formed the structural core, adding strength to the interior, while sandstone was used in parts of the foundation to help distribute the tower's weight. However, the soft clay and sandy soil beneath caused the famous tilt. To bind the stones, lime based mortar was used, ensuring cohesion and durability. Despite the high quality materials, the unstable foundation led to the tower's unintended lean. By the time the third floor was completed, the tower began leaning due to the marshy soil beneath its foundation. As I have told before, that stronger foundation leads to a stable and strong building, but as for the Tower of Pisa, the foundation was shallow and it was just 3 meters deep, and it could not support the weight of the limestone and marble structure.
अगर हम materials की बात करें तो Leaning Tower of Pisa is a marvel of medieval engineering that was built using a combination of materials. The primary material utilized are white and grey marbles and limestone that add weight and strength to the overall building. The inner layers of the wall consist of rubble masonry bound with lime mortar, a common medieval construction technique. This mixture provides durability and a degree of flexibility, which has likely helped the tower survive over the century. Lead weights were later added to counterbalance the tilt. Iron clamps were used to hold stone together during construction, providing additional stability. If we talk about the mass distribution, the tower's tilt has caused its mass to become unevenly distributed. The lower side of the structure carries significantly more weight due to the lean, creating increased pressure on the foundation in that area. The tower's hollow cylindrical design helps distribute its weight outward to the supporting column rather than concentrating it in the center. This design reduces stress on any single point of the foundation. The base is constructed with thicker marble and masonry, making it heavier to stabilize the structure, whereas the upper level taper and are lighter, reducing the load as the height increases. The tower's slight flexibility due to the lime mortar and masonry allows it to adjust subtly to stresses, which has helped prevent collapse. Interestingly, the soft foundation soil, though initially a problem, has paradoxically helped the tower survive earthquakes over the centuries. The soil absorbs seismic shocks, preventing resonance and the collapse. These materials and the careful distribution of mass contribute to the tower's resilience and enduring fame as an architectural icon.
Despite the challenges faced by the builders due to the tower's lean, they tried to adapt their construction techniques to stabilize the structure and preserve its architectural integrity. For this purpose, they adapted modern stabilization techniques. In the 1990s, engineers employed a method called soil extraction. By removing soil from beneath the higher side of the tower, they reduced the tilt from 5.5 degrees to 3.97 degrees. Counterweights of over 600 tons were also added to stabilize the structure during this process.
Over the centuries, several structural adjustments and modern engineering solutions have been implemented to stabilize the Leaning Tower of Pisa and further prevent tilting. In the 1990s, engineers added lead counterweights totaling 800 tons to the base of the tower on the higher north side. These weights acted as a counterbalance and prevent further movement. In the 1990s, steel cables were temporarily attached to the tower to prevent it from tilting further during restoration efforts. These cables anchored the tower, ensuring stability while corrective measures were taken. Concrete and ground injections were used to stabilize the weak soil beneath the foundation. ऐसे करके फाउंडेशन को भी reinforcement दी गई थी. This strengthened the clay and sand layers, reducing the risk of further subsidence and sinking. कुछ sections of the building में engineers carefully adjusted the center of gravity by removing some heavy stones and replacing them with lighter materials.
Although the apparent instability of the tower suggests vulnerability, its flexible construction allows it to withstand the seismic forces. Its hollow interior and relatively lightweight materials like polyurethane foam and fiber reinforced composites were used. They reinforced or stabilized parts of the structure while ensuring minimal impact on its original design. These materials helped absorb vibrations, reducing the risk of collapse.
As time passes by, the building must be at risk of further tilting. किस तरह से architects and engineers ने इसको preserve करने में efforts किए हैं?
Architects and engineers are preserving the building by monitoring it. The tilt is now stabilized at 3.97 degrees and constant monitoring is performed to detect any movements. ये monitoring sensors or GPS devices के through की जाती है that tracks the shift in the structure or foundation.
From the intricate design of Sagrada Familia to the towering ambition of Burj Khalifa and the accidental tilt of the Leaning Tower of Pisa, these buildings showcase the power of engineering and ingenuity of architecture. हर structure एक unique story बताती है, that how they overcame those challenges and how human intellect pushed boundaries. We can learn from these stories and apply it in our architectural practice.
Thank you for joining us on Archi Talk Shop. That's it for today's journey through the Leaning Tower of Pisa, Burj Khalifa, and Sagrada Familia, the icons of resilience, ambition, and artistry. Until next time, keep shaping the future, one structure at a time.
And remember, every building has a story. You just have to look closely enough to find it.